In the previous lecture, we were discussing about the definition of a complex potential function which is inclusive of the velocity potential and the stream function. What is the commonality between velocity potential and stream function? That also we need to discuss very carefully. So, one interesting confluence that we have already discussed is that except for the stagnation point they are orthogonal to each other. The other important fact will come out if we consider the two dimensional incompressible plus irrotational flow. So, you have u equal to del psi del y. So, for two dimensional plus incompressible flow, for irrotational flow curl of velocity is a null vector which is equivalent to the following two dimensional situation. What is that two dimensional situation? Right. So, this if you substitute u and v from here, okay. So, this is clearly the Laplace equation in two dimensions. So, you have this equal to 0, and for two dimensional irrotational flow okay. So, for incompressible two dimensional and irrotational flow, if you add incompressible, okay. So, this leads to interestingly both psi and phi satisfy the Laplace equation in 2 dimensional plane. So, if we write that phi del square phi equal to 0 and del square psi equal to 0, we can also write del square phi plus I psi equal to 0, right. So, that means we can use the complex potential function as a basis to capture the variables, field variables phi and psi. Okay. This is number 1. Number 2 is, if f is equal to f1 is a solution and if f is equal to f2 is a solution, so you have okay. Then f1 plus f2 is also a solution. Not only that, if there could be f3, f4 whatever, you could have that as a solution just by simply adding. This linear superposition works because Laplace equation is a linear partial differential equation, and Laplace equation is a beautiful equation because from a mathematician or an applied mathematician's perspective it might have different applications, but generically it has this template form, whereas from the point of view of physicists and engineers it can be applied on one side to solve problems in irrotational flow, in fluid mechanics, on another side in electrical engineering to solve the electrical potential distribution where there are no volumetric charges. So, in such a situation you can clearly see that the Laplace equation can address a wide range of physical problems, and therefore solution of Laplace equation is very, very important in applied mathematics community. So, what we do here is simply use the superposition, and this superposition gives a very simple elegant way of approaching the Laplace equation. So, what we will do is we will try to find out the functions f1, f2 etc. for simple types of flows, say uniform flow. Uniform flow is the simplest inviscid and irrotational flow. So, we will try to find out the function f, say f1. There are other types of inviscid and irrotational flow, very simple flows which will give these complex potential functions f2, f3 like that. Eventually we will build up on the system by considering a superposition of those things, and what will be our objective? Objective will be to solve for phi and psi. And why phi and psi are important? Remember from our earlier discussions that the contour of a body itself is a streamline. Why the contour of a body is itself a streamline? The contour of a body is itself a streamline because by definition of a streamline there cannot be any flow which penetrates through it, and a physical body cannot be penetrated by a fluid until and unless there are holes in the body. Okay. So, what we may recognize out of here is that by obtaining stream functions we can also make or solve an inverse problem, that what could be the contour of a body past which the flow is being described by the stream function, because a special case of a stream function which say we will set as 0 will represent the contour of the body. So, for example, if we say what will be the nature of potential flow past a circular cylinder. Okay. So, to understand that we can make a superposition of certain simple types of this potential F, elementary types of complex potential F, superimpose them together and try to obtain a contour of a body which looks like a circular cylinder. So, the objective will be that what superposition gives the flow past a circular cylinder, what superposition gives flow past an elliptic cylinder, these kinds of questions we will try to answer. So, we will start with the first example, uniform flow. So, to model a flow, actually we are interested about the stream function and the velocity potential. Here what we know the velocity, uniform flow we know the velocity, right. So, let us say that the uniform flow is like this, which is making an angle alpha with the x axis and this is x axis and this is y axis and this is u infinity. So, u is u infinity cos alpha and v is u infinity sin alpha. The objective is what is the complex potential corresponding to this. What we know is df dz is u minus iv, right. If f is phi plus I psi, then df dz is u minus iv, this is what we have derived. So, this is u infinity cos alpha minus I u infinity sin alpha. So, u infinity e to the power minus I alpha, right. Let us take a simple example, special case alpha equal to 0, that is uniform flow along x axis. So, that means you have df dz is u infinity. So, f is equal to u infinity z plus a constant, you can set always that constant equal to 0 as a basis. So, this is u infinity into x plus iy. So, this is phi plus I psi. So, isolating the real and imaginary parts, phi will be u infinity x and psi is equal to u infinity y. Okay. So, let us try to draw the phi equal to constant lines. So, what are phi equal to constant lines? Phi equal to constant lines means x equal to constant lines. X equal to constant line means like this. These are phi equal to constant, and psi equal to constant means y equal to constant, that means these are parallel to x axis. So, this is psi equal to k1 okay. So, this is also called as a flow net with the orthogonal phi's and psi's are together laid out to form a network. So, this is the most simple type of flow, but at least we can get a potential, complex potential F is equal to u infinity z for uniform flow along x axis. Okay. Before getting into the next example, which may demand the use of polar coordinates, we will try to write the function df dz in terms of polar coordinates. So, df dz in terms of polar coordinates. So, now you have instead of uv as a component, you have Vr and V theta as component, same thing but expressed in r theta coordinate form, where this angle is theta. So, what is u? U is, now you make you resolve Vr and V theta along x and y. The resolved components along x together will be u and along y together will be v. So, u will be Vr cos theta minus V theta sin theta, and V is Vr sin theta plus V theta cos theta. So, recall that df dz is u minus iv, which we wanted to write in terms of Vr and V theta. So, u is Vr cos theta right. Vr minus I v theta, if you take as common, it will be cos theta minus I sin theta, right. So, this is Vr minus I v theta into e to the power minus I theta. With this in purview, we will consider our next example, which is called as point source. What is a point source? A point source is a point from which you have a radial spreading of flow. If the source is at the origin, say this is 0 comma 0 as an example, then the velocity distribution reads Vr is equal to c by r and v theta equal to 0. So, at r is equal to 0 you have a singularity, but close to r equal to 0 you have very high radial velocity, and the radial velocity decreases with 1 by r as the radial location increases. Now, this being abstract, what is not abstract is what is the flow rate that you are getting out of this. What is the flow rate? At a radial location small r, let us say this is radial location small r, what is q? The length perpendicular to the plane of the figure is 1. So, q Vr into 2 pi r. There is no need of breaking it up into theta elements, because Vr is not a function of theta, Vr is a function of r only. So, Vr is c by r into 2 pi r, and therefore, it is 2 pi c, and this gives rise to an interesting observation that the flow rate is not a function of r, although the velocity is a function of r, but flow rate is not a function of r. So, this we can write a universal flow rate q. So, the constant c can be replaced by a more meaningful parameter q by 2 pi. So, in this scenario, we can use the polar coordinate more effectively. So, Vr is q by 2 pi r minus I v theta is 0 into 1 by e to the power I theta, right. Now, what is r into e to the power I theta? That is the z complex number, right. R z, the equivalent representation of the complex number in r theta plane is, because e to the power I theta is cos theta plus I sin theta. So, and this is r cos theta is x and r sin theta is y. So, this is x plus I y. Okay. So, this we can write q by 2 pi z. So, what is the corresponding f? dz by z is ln z. So, we can sum it up and say that the f, the complex potential function f for a source will be related to the flow rate. So, this sometimes is called as strength of the source, strength of the source. So, q by 2 pi ln of z. What happens if instead of a source it is a sink? So, let us consider that if it is a sink of strength q, the same thing remains, just q will be replaced by minus q. What happens if it is a source of strength q located at x equal to a? What it will just require is a translation of coordinates. So, let us define capital X is equal to small x minus a. So, when small x is equal to a, capital X will be 0. So, in the capital X coordinate it becomes same as this. So, this will be f is equal to q by 2 pi ln capital Z. And z is x plus I y. So, here y is 0. So, q by 2 pi ln capital X. So, this is q by 2 pi ln x minus a. Okay. Similarly, wherever the source is located, you can make a shifting of the coordinate system. So, if it is located on the y axis, you at y equal to b, you introduce a capital Y is equal to small y minus b. No, no, this is x, this is y, this is on the x axis only. This is yes. Oh, sorry, yes, right. Oh, here, right. Plus I y is anyway 0 for this. So, why it is important to include plus I y is because this f is a complex potential function, right. So, it should generically include the y component also. So, but it does not matter really for this example, The reason is that this Z is based on you know the combination of x and y. So, the special case where the source is lying on x axis or y axis, the special cases are treatable by reducing it to either x or iy. So, if it was located on y axis, then if it is located along x axis, this z will be simply x. If it is located on y axis, it will be simply iy. Okay. So, this z is the basically the so what I mean is not this z but this one, this one. So, this will be either, so let us take the example of y axis for example, that will make it more clear. So, that will be z minus so capital Y okay. So, if you now write so your new z will be x plus new iy. So, x plus iy minus ib, that is what I want to mean, that this is not disturbed, this remains z, but what is disturbed is either on the x axis it becomes a or along the y axis it becomes ib, right. So, what I have written here is this is plus iy you have to add. So, z is x plus iy, only x is shifted, x becomes small x minus a. So, small x minus a plus iy, plus iy is anyway there, that is the definition of x. So, in terms of the variable you have x plus iy which is z and minus a is isolated which reflects where it is kept. So, this is really not, this x has to be added with plus iy, but the location is reflected by this one. So, to sum it up we can say that if you have f is equal to q by 2 pi ln, this part will be there because either x is shifted to x plus something or y is shifted to y plus something, but the definition of z as x plus iy remains. So, both x and y will be there, plus it will be a shift, right. So, here q by 2 pi ln not just x, x plus iy, that needs to be carefully brought in because z is by definition not just x, it is x plus iy. Okay. Okay. So, we stop it here, and in the next lecture we will continue with more examples on superposition of these basic flows. Thank you.